Welcome to Summarize Science. Today we are looking at a fascinating new way researchers are using artificial intelligence to sharpen our view of the world's weather. Climate data is often collected at low resolutions, which can make it look blurry and hide important details about local storms. While AI has been used to enhance video quality for years, applying it to climate science is incredibly difficult. Most deep learning models are designed for just one specific scale, meaning they are rigid and hard to reuse for different datasets. Researchers often have to completely redesign their AI architectures every time they want to look at a new resolution. To solve this, a new scale-adaptive framework has been developed that can handle many different factors at once. The goal is to develop a versatile architecture that can learn to upscale data regardless of the specific spatial or temporal ratio. This allows for much more flexibility when dealing with information from satellites, radars, and ground stations. The system works in two distinct stages to ensure both accuracy and realism. First, a deterministic model predicts the conditional mean, which is basically the AI's best guess at the average rain pattern. Then, a residual diffusion model adds back the high-frequency details and fine textures that make the weather look real. To keep the results physically grounded, the researchers implemented an optional mass conservation transform. This ensures that the total amount of precipitation remains the same in both the low-resolution input and the high-resolution output. This prevents the AI from accidentally creating or destroying water during the upscaling process. The framework is described as scale-adaptive because it only requires retuning 3 specific hyperparameters for different tasks. By adjusting the attention length and the noise schedule, the same model design can be used for vastly different resolutions. This is a major improvement over older methods that required starting from scratch for every new project. The team tested their framework on a massive dataset of precipitation over France called CUM4. This dataset includes radar and rain gauge observations at a very high resolution of 1 kilometer and 1 hour. They also included topographic data so the AI could learn how mountains and terrain affect rainfall patterns. In the results, the AI demonstrated it could span super-resolution factors from 1 to 25 in space and 1 to 6 in time. This means a single blurry pixel could be accurately expanded into hundreds of high-detail data points. Visual examples show that while different scenarios generated by the AI vary, they all capture the large-scale evolution of the storm. Quantitative benchmarks showed that the full architecture significantly outperformed standard baselines like bicubic interpolation. The diffusion model was especially good at capturing extreme rainfall events, which simpler models often smooth out or underestimate. By representing high-frequency variations, the AI provides a much more realistic view of how intense a storm might actually be. The researchers found that as the upscaling task gets harder, the AI needs slightly more context from the past to perform well. However, they noted that information from more than half a day ago is rarely significant for predicting current precipitation. This allowed them to optimize the model for both speed and accuracy. To recap, this new framework provides a reusable recipe for upscaling environmental data across many different scales. It combines the stability of traditional regression with the realistic detail of modern diffusion models. In the future, this could lead to foundational models that share weights across many different geographical regions. Most importantly, it could provide the high-resolution data needed to better predict flash floods and protect communities. Thank you for watching Summarize Science.